Hello everyone. Today I would like to present a paper called Cyber Physical Automation System Modeling with IEC 64099 for their formal verification. Okay, let's move on to contents. In introduction, we will discuss the verification and validation challenges in automation system. Then we discuss a case study in detail. After that, we see how the tool chain tackled these challenges by introducing a problem-oriented notation for closed-loop models of cyber-physical systems in IEC 64099 standard. Finally, we will discuss results and future goals. Now let's see the introduction. Identifying possible flaws in automation system composed of mechatronic objects with embedded logic is quite difficult. So how to tackle the challenges? Maybe we can run the system in real, but it's more expensive. And also while running some process may even cause severe damage to the system. Therefore, we can construct a simulation model of the real system and see how it behaves. But there are intermittent errors, which do not show up in simulation but suddenly appear in real behavior. Simulation can show the presence of bugs, but doesn't prove their absence. So what we do next? Formal verification could be used as a better approach. Formal verification is the act of proving or disapproving the correctness of the algorithm with respect to the given property or specification. In order to do the formal verification of the system, we need to convert the automation system to modeling language. Now let's see how formal verification of cyber physical systems is done. We can convert IEC 64099 function blocks to SMV via FB to SMB tool. We will discuss FB to SMB tool in upcoming section. Control function blocks of real system in IEC 64099 can be converted with the help of this tool. But in order to verify the complete system, we need plan model and it should be connected. Plan model, which is constructed for simulation, can be used to create a formal model, but the resulting model may be too complicated. In the past, previous researchers used to develop a simplified model of the plan manually and then somehow integrate with the model of the controller generated by FP2SMB. To address this issue, we invented the notation in IEC 64099 for discrete state modeling and the methodology for simplifying the hybrid simulation model to discrete state model. We also constructed a tool chain which combines design, simulation, and formal verification. So let's see the formal verification of a real experiment with the help of this tool. Case study. The Industry 4.0 vision is to compose production systems from autonomous assets. The drilling station shown in video also consists of the same. The first mechatronic component is a drill which moves in upward or downward direction. Whenever a workpiece is detected by a sensor under the drill, it moves downwards and starts drilling. Once it completes drilling, it moves upwards and rests at the home position. Second one is table, which rotates from one fixed position to another. The cycle is completed when it rotates 6 times. When a workpiece is placed in the loading position, the table rotates to bring it under the drill. Deploying control logic directly in real system may be too expensive because bad design of control logic may cause damage to the mechatronic components. Now let's see how simulation model implementation of the system helps in this scenario. In order to implement simulation model, the controllers are connected exactly same way as in the real configuration. The visual representation of the simulation process and function block configuration in deployment and simulation shown in figure. Development of visualization CADs is done with the help of NST Studio developed by NST Control. Simulation helps to understand the behavior of the system and it also helps to show the errors identified during verification in simulation. However, there are some intermittent errors which do not appear in simulation but occur in real system operation. To tackle this scenario, we use formal verification. Formal verification. Compared to simulation, formal verification helps to computationally explore more scenarios in the system behavior. Formal verification can be done by a model checker tool called NuSMV. NuSMV can check the system behavior by verifying various specifications, and if the specification doesn't hold true, it produces counterexample. In the past, model generators were developed to convert IEC 64099 function blocks to such models. FB to SMV can be used for this purpose. However, applying FB to SMV to simulation model in IEC 64099 results in complex untractable models due to continuous dynamics. So we need to transform the simulation model to discrete state domain in order to do formal verification on the system. Let's see discrete state modeling approach. We convert the simulation model to discrete state model with the help of a non-determinism. After that, we substitute the simulation model with a discrete state model. Let's see the discrete state modeling approach in detail. In order to implement simplified and accurate plan model for formal verification, we use discrete state modeling. The discrete state equivalent of the simulation configuration is shown in figure. Here the function blocks simulating the drill and table substituted by their analogous operating in the discrete state domain. Conversion of hybrid state machine to discrete state model is shown in figure. The core part of simulation model is a hybrid state machine describing the continuous dynamics of mechatronic components. We propose a methodology to discretize it and add non-determinism, but structure of the state machine remains the same. Let's see discrete state modeling in plant. Notation for plant modeling. State machine implementation of drill model is shown in the figure. In our model, we use NDT in the transition from the motion state DD move to the static state XT end. NDT helps to provide unknown duration of the motion from one state to another. Plan may fail. The forward and backward signals becomes true simultaneously. So we introduce an error state which helps to identify whether the controller creates this scenario. Let's see the non-deterministic transition in controllers. Non-deterministic transition is helpful for the simplification of controller models containing timers. In the drill, the drilling process needs to be done for several duration, which is achieved with the help of E-delay function block. The composite function block consists of real controller and E-delay function block is shown in figure 5. However, formal modeling of the timers in SMV is computationally hard. Delay can be substituted by NDT signal. Therefore, we removed the timeout E-delay and added NDT as an input. The execution control chart of the drill controller and the modified drill controller is shown in figure 6. Now we can model the non-determinism in SMV. SMV provides a way to accomplish non-deterministic choice by providing a set of values to the signal. The first statement is used to declare the variable entity as a Boolean type, and second statement is used to initialize entity variable to either true or false value. In every transition, we are giving a provision to choose either true or false. This makes entity variable unpredictable in each transition. Implementing non-determinism in every transition can be limited by introducing conditions in a statement. If it's not required for the entity variable to choose values in every transition, we can design like this. We already constructed the discrete state model of the plant and also connected the plant model with the same controller in exact same way as in the real configuration. In order to verify the system, we can use this toolchain. NST control provides a function blocks in XML format, and these files give as an input to the FB to SMV converter, which converts the function block to SMV code. The SMV code is then fed to the NuSMV model checker for verification purpose. NuSMV checks the CTL specification. If the specification is wrong, then the NuSMV produces counterexample. To make the specification true, we need to analyze the counterexample provided by NuSMV. But identifying the variables changed in each iteration is difficult. The NuTrack tool provides a better way to understand each state by converting counterexample to CSV file. FB to SMV tool generates SMV model from function blocks. IEC 64099 function block expressed in XML format is given as input, and it generates SMV code with the help of ASM semantics. The tool converts basic and composite function blocks and also includes more additional features like limiting the boundaries of variables to reduce state space, changing the execution order of FPs, deciding the input event priority by changing the order, etc. The proposed non-deterministic transition notation has been added to the tool as a result of this work. Results and analysis. The formal model of the system was verified with the help of CTL specifications. While testing CTL specification in NuSMV, we found that the first statement is false, so it is possible that the table can rotate while the drilling process is going on. While executing the specification, the NuSMV gave a counterexample that contradicts this statement. The counterexample generation for the specification took 26,000 seconds to complete. We tested the same logic in simulation model, and the table rotated from its current position to another while drilling the workpiece. The rail system also exhibits the same issue. We fixed the issue by analyzing the counterexample. After that, we verified the CTL specification again, and this time NuSMV gave the true result. The modified controller is tested in real object as well as in simulation system, and it was behaving as we expected. That is, table was not able to rotate while drilling is going on. In order to identify whether the controller produces forward and back signals true at the same time, the second specification is used. After executing the second specification, the NuSMV produced output as true. The ECC of a drill model never goes to error ECC state, that is, controller never produces forward equal to true and back equal to true conditions simultaneously. Conclusion. In this paper, we proposed a toolchain which helps to verify and analyze the function blocks implemented in IEC 64099 standard. This tool can be used for continuous development and evaluation of distributed control system. The accurate implementation of formal model is necessary to identify all possible flaws in the system. The existing functionalities of FP to SMB along with non-deterministic transition in function blocks helps to provide a similar formal model of the system. The developers working on complex system design can use this toolchain for continuous development and testing. Future work. The non-deterministic transition in function blocks can be extended by introducing entity as a variable to the function blocks. This entity variable can be of any IEC 64099 data type, but the entity variable should be able to choose one value from set of values. For example, if we introduce entity variable as an integer data type and its values limited 0 to 5, then it should be able to randomly select one value from 0 to 5. In order to introduce more randomness to our formal model, it's better to implement entity as a variable instead of entity as an event signal. An interesting field to explore is if we can generate the specification as well as plan model automatically, then the existing manual interventions can be avoided. The toolchain which identifies all possible errors and fixes them automatically could be the next step in future. The models used in this paper are not based on time. So the timing problems due to different set of timescales of the controller and plan cannot be identified by this approach. The extension of notation to timed automata can be added for future work.